Hello, everyone. I am Giulia Giannini. I am a PhD student at the DES-Y Institute in Barcelona.
And I am Martín Rodríguez Monroy, PhD student at CIEMAT in Madrid. And in this presentation, we're going to talk about photometric redshifts and observational systematics on the DES-Y3 analysis. So the Dark Energy Survey is a photometric survey placed at Cerro Tololo in Chile at the Victor Blanco 4 meters telescope. It has taken data since 2013 to 2019 and covered about 5,000 square degrees in 5 different photometric bands, reaching magnitudes of up to 23. In the GR3 analysis, we have measured the positions and shapes of more than 100 million galaxies. So in DES, we measure 3 different correlation functions to maximize the cosmological information that we can obtain and also to better constrain systematic effects. These correlation functions are the cosmic shear, which measures the correlation between shapes and shapes of galaxies, galaxy clustering, that measures the correlation between positions and positions, and finally, galaxy-galaxy lensing, that measures the correlation between positions and shapes. To do this, we use 2 different samples of galaxies. Source galaxies, on which we determine the shapes, and lens galaxies, on which we measure the positions. We are going to focus on the lens galaxies. As an additional level of robustness to our results, we have used 2 different lens samples. The red magic sample, that is formed by luminous red galaxies with very high quality photometric redshifts, covering the redshift space between 0.15 to 0.90 and containing about 3 million galaxies. And the Maclean sample, which is the fiducial GR3 sample, that contains about 11 million galaxies, but in turn has a lower signal-to-noise. This sample is computed by applying a cut in magnitude I as a function of the photometric redshift. The photometric redshift is determined with the DNF code, and this sample contains 6 tomographic beams, whose edges have been optimized to perform cosmological analysis. Now we are going to focus on the main sources of systematic errors in galaxy clustering. We are going to start talking about observing conditions and astrophysical sources. As astrophysical sources, we understand the dust extinction caused by the dust in the Milky Way or the stellar density. And as observing conditions, we understand the conditions at the moment the images are taken, for example, the scene, the exposure time, etc. In order to characterize these effects, we use survey property maps, which are Hill-Peaks maps that track the spatial variation across the sky of these quantities. In the year 3, we have 107 of them, and the point is that correcting by too many of them can lead to overcorrection, while using only a few of them can lead to undercorrection. As I will explain in a minute, we apply correction methods that obtain the level of contamination of each map in a data-driven way, but before that, in order to optimize the processes, we have to perform a dimensionality reduction. We have used 2 different approaches to this. First of all, Pearson's correlation matrices, but the fiducial choice was to calculate a principal component analysis of the 107 maps, obtaining principal component maps and retaining only the 51st one of them, since they explain about 98% of the total variance. On this subset of maps, we apply our correction methods. The methods that we apply to and that we employ to correct the data are iterative systematic decontamination, or ISD for short, which is an iterative method that evaluates the significance of each survey property map and correct for them stepwise. The level of contamination is obtained by computing what we call the 1D relation, which is the relationship that exists between the observed galaxy number density and the value of the survey property maps at each position of the sky. The second method is elastic net, or ENet for short, that performs a multilinear fit to all survey property maps simultaneously by doing an elastic net regularization, which is basically a ridge regularization plus a lasso regularization. Both methods produce weights that are applied to the data in a multiplicative way. ISD is the fiducial method to decontaminate the data, while ENet is used as a robustness test to ISD using log normal mux and also as an estimation of the systematic uncertainty that we have to take into account in the final covariance. So in summary, iterative systematic decontamination works as follows. We have to fix before a threshold for the 1D contamination. Then we define the 1D significance by evaluating the 1D relation of each survey property map, not only against the data, but also against log normal mux. Once we have determined which map has the highest significance, we fit each 1D relation with a linear function, and we define a weight map as the inverse of that function. Those weights are applied to the data multiplicatively, and we make sure that the effect has been removed. Then we go back to the beginning, we reevaluate the significance of each Sabel property map, and the process is repeated iteratively until all maps have a significance below the threshold that we have fixed. This has been applied to both MacLim and RedMagic, and also to the VAO sample, which is an additional sample devoted to the measurement of the VAO scale. So this animation summarizes the process. In the x-axis, there are the 50 principal component maps that we are considering, and the y-axis represents the significance or level of contamination of each of these maps. So ISD identifies the level of contamination and corrects for the most contaminated map at each step, until all of them have a significance below the threshold that we fixed at the beginning. Once the correction has been obtained, we need to validate it, and we do this by checking the potential biases introduced by the ISD method. The first source of bias that we evaluate is the false correction bias, which is associated with chance correlations that can lead to overcorrecting the data. To determine it, we use mocks with no contamination added, and we conclude that this effect is negligible. The second source of bias, which is the most important one, is the residual systematic bias associated with contamination that is not properly corrected. To determine this, we use INET, and what we do is to run INET on the data, obtain weights, and use the inverse of those weights as a contamination to produce mocks with contamination added. Then we run ISD on those mocks, and in this way, we determine whether both methods are sensitive to the same modes of contamination. This bias is taken then into account as a systematic contribution to the final error budget. We also take into account a subdominant component that comes from running both INET and ISD on the data and evaluating the different answers that both methods give. So in this figure, the yellow region corresponds to the covariance matrix with no systematic effects added, while the blue region corresponds to the same covariance matrix after accounting for the systematic contributions. Once this is done, we evaluate the effect of these biases in the estimation of cosmological parameters with mocks, and we determine that the biases imparted on this parameter space are negligible. Finally, as an additional level of robustness, we obtain weights with different configurations of ISD and INET, and we also introduce alternative methods such as neural net weight, and we conclude that we always recover the same clustering amplitude within the statistical uncertainty. So finally, here are the DES-Y3 results for galaxy clustering. So the red crosses correspond to the angular correlation function from the data with no correction applied, while the gray points correspond to the same correlation function after having applied the weights to the data. If we now focus on the fourth and fifth redshift bins of MacLim and RedMagic respectively, which are the ones where the difference between correcting and not correcting is more important, we can illustrate how dramatical this effect is on the estimation of cosmological parameters. So the red contours correspond to constraints on galaxy bias parameter and omega matter parameter from data with no correction added, while blue and orange contours correspond to the constraints on the same parameters after having applied weights from different configurations of ISD. Once we have obtained a correcting measurement of the galaxy clustering, this is ready to be combined with galaxy-galaxy lensing measurements to obtain the 2x2pt probe. This probe is more sensitive to the total matter density or omega matter parameter. Once we determine that the 2x2pt measurement is statistically consistent with the cosmic shear measurements, which are more sensitive with the clustering amplitude, we can obtain the 3x2pt probe that provides very tight constraints on cosmological parameters. In particular, the DES-Y3 analysis has a factor of 2.1 improvement in signal to noise with respect to the GR1.
Thank you, Martin. So another source of systematic errors for galaxy clustering are photometric redshifts. We know that galaxy clustering is particularly affected by the higher moments of the NOZ, so we have to take great care in assessing those systematics. We have mentioned that for the Y3, we use two sets of lenses, and while RedMagic has a higher signal to noise, MacLim was constructed to yield a larger number of galaxies, and therefore it is noisier. So it is necessary to further calibrate its redshift distributions. And the fiducial methodology for Y3 was that We estimated the NOZs using the DNF code and shifted and stretched that estimate to match the cross-correlation measurements. In this work, we want to apply a similar methodology than the one used for the source sample by combining a cross-correlation and phenotypic calibration to allow a marginalization over the full shape, as opposed to only on the shift and stretch parameters only. So this is our pipeline, and we will start with SOMPZ. The main motivation is that in photometric surveys, we only have a few bands, and try to distinguish different SEDs of different galaxies is very difficult. And type redshift degeneracy, precisely for this, is one of the main causes of uncertainties in redshift calibration. So if we have extra bands available in deep fields, then this can help break this degeneracy. The only problem is that these extra bands are available only for a subset of our galaxies. Another tool that we need are self-organizing maps, which are neural networks producing a discretized and lower dimensional representation of our input space. So we can use this in the SOMPZ method to classify galaxies by their fluxes, and we can do that pretty accurately since we have these extra bands from the deep fields. So our SOMPZ methodology stands on grouping our galaxies in a wide and deep SOM, and validating the redshifts in the deep SOM through high-precision redshift samples, and then transferring back this information into the wide SOM using this transfer function, which is provided by Barrog. That is a code that injects many times deep field galaxies in real DES-Y field images. The main uncertainties of this methodology, of course, are related to the deep fields. So we have sample variance due to the limited area of the deep fields, 9 square degrees compared to 5,000 square degrees of the full wide field. And of course, also shot noise because of the limited number density of this deep field sample. You can see that this is the dominant uncertainty in the plot on the right. The final product of our calibration is a set of NOZ realization, like 1,000 realization, that overall span all the uncertainties that we think are included in our SOMPZ methodology. Now we can move on to clustering redshifts, that instead is an independent methodology that it exploits spatial overlap between your target sample and a high quality redshift sample that we are calling reference. And if we bin the reference sample into thin redshift bins and cross-correlate each of those with your target sample, you can obtain your signal. The main quantities into play here are the galaxy matter biases of the two samples, the dark matter clustering, and the magnification term. So in the way we estimate our uncertainties was developed for DES-Y3. So we forward model the full clustering signal, and we multiply our model by the systematic function that is a smooth function flexible enough to fully characterize our uncertainties from the fact that we ignore the redshift evolution of the galaxy bias and failures in the linear bias model that may happen at low scales. We also have 2 parameters that appear in the magnification term. So from this, we can assign a likelihood of our measured cross-correlation given redshift distribution and our parameters. So we marginalize over 2 sets of parameters. The first are the S parameters of the systematic function, and the other ones are the bias and the alpha of the unknown sample of the maglim appearing in the magnification term. And here we are assuming this bias and the bias englobed by the systematic function to be different. And we assume the bias in the magnification to be constant, since magnification anyways is only significant in a limited restricted redshift range. So we can ignore the redshift evolution. In any case, we have shown that magnification is negligible. So we can then combine the two methodologies, and we sample our NOZs from a joint likelihood. And as you can see, clustering redshift is able to improve the constraints on the shape of the distribution and produce a smoother NOZs. So as we have said, these things are particularly precious for our analysis for galaxy clustering and galaxy-galaxy lensing. So this is a great improvement in the methodology. If we compare with the fiducial results, so there is a good compatibility with the fiducial estimate from DNF, although the SOMPZ and plus WZ provide a more accurate estimate by construction, and especially on the tails. By looking at the simulated data vectors, for now at least, we simulated a potentially realistic scenario where the true NOZ are slightly different from the NOZs that we are testing. And we are comparing two different marginalizations. So the first is the fiducial, marginalizing over a shift on the mean and a stretch on the width of the average SOMPZ plus WZ realization. And then the full shape marginalization, so that at each step of our chains, we are sampling out one realization out of the ensemble using the hyperrank code to optimize and make more efficient this sampling. We obtain slight differences at the level of 0.5 sigma, and one other maybe more interesting difference is that we found less correlated biases for the full shape marginalization. So since this is the only difference in these chains, we think this must be driven by the way we are accounting for the higher order moments in the NOZs. So we believe that for our modeling, the hyperrank full shape approach is the most correct. And we have tested also that we are recovering unbiased parameters also in buzzer simulation. So to conclude the talk, so as the area and depth of photometric surveys increase, the statistical errors are drastically reduced. And of course, this means that it is even more crucial to correctly characterize the systematic effects. In this talk, we have presented new techniques that helps us to improve our treatment of systematics, both on the photometric redshift calibration side and on the correction of observational effects side. We have said that these are two of the most challenging sources of error for both the current surveys as the dark energy survey and for the next generation ones. So thank you for your attention, and we hope to see you at the discussion.